Now let's talk about an experiment that led to the central idea behind our modern picture of atomic structure. That central idea is something called wave-particle duality, and that is things like electrons can act like waves in some circumstances and particles in others. And this experiment showed that that was true of light, which we thought was a wave phenomena. All right, so here's the effect. It's kind of technologically important. We've got a metal. You would think sodium metal, let's say. You would think a metal would be a lot of sodium atoms, if it was sodium metal. But it's not. It's a lot of ions that have given up their electron. They've got one electron on the outside of the atom that's held on very loosely. So when you have a metal, what you have is a whole bunch of ions, metal ions, that have let go of one of their electrons. Now, those free electrons act like glue. They glue all the ions together. And this model of metals explains a lot of the properties that metals have. If you hit this with a hammer, you're going to change the arrangement of the sodium ions, but the electrons will instantly rearrange so that they're still gluing together the sodium ions. So you can hammer on a metal and hammer it out into thin sheets, and the free electrons keep it glued together. This model also explains things like why metals conduct electricity so well. If you pop an extra electron in on this side, in order to stay electrically neutral, an electron can just instantly pop off on that side. So without even traveling through the metal, the electron can appear on the other side of the metal, and it looks like the electron moved very quickly from one side of the metal to the other. These free electrons are quite easy to pry out like that. And one of the things that you can do is send an electromagnetic wave in. And an ultraviolet wave will work particularly well. And this will cause the electron to start to oscillate enough to shake it out of the metal. And this gives us a way to measure, experimentally measure, how much energy a light wave is carrying. The electron here is going to fly out. I'm going to write it as E-. I'm going to call it a photoelectron. Because it was kicked out of the metal by light. Now, let's look at how we can experimentally measure the energy of the light beam with this. It is pretty easy for you to measure an electric current here because you've got a flow of electrons. So you can hook a little meter up to this, connect the electric current, or measure the electric current, and that will tell you how much energy these photoelectrons have. So you can find the energy of the photoelectron. It'll be its kinetic energy, its energy of motion. Easy to measure. If you wanted to relate it to the actual photoelectron, kinetic energy is 1/2 mv squared, where m is the mass of the electron and v is the speed. So the more energy that this thing has, the more speed it's got, and the bigger the electric current that you would measure. So it's easy to get that experimentally. Now, the energy of the light per photoelectron you can get by making a little energy budget. So this is the energy you're pumping in. The photoelectron is taking some energy out, but there's another item in the budget that we have to include, and that is how much energy does it take to pull this electron away from these sodium ions, because they're hanging on to it because they have a positive charge. So you're going to have to put some energy in there to get that that electron out. We're going to call that the threshold energy. It's the energy that's required to pull an electron out of the metal. Now, people in physics call this threshold energy a work function for the metal. So that has another name. Sometimes if you're looking at another book, sometimes you will see them call this the work function. And they'll even give it a symbol. Sometimes they'll call it a phi. You don't have to know that, though. This energy budget is kind of the key to the experiment here. We're trying to measure the energy of the light that the light contributes to kick out one photoelectron. And it's equal to the energy of the photoelectron that gets kicked out. It's a kinetic energy. Plus the energy that it takes just to remove an electron from the metal. So, what do we expect to happen here? You'd expect that the energy of the light would depend on the amplitude of the light. Why do we expect that? Well, we said that before. Remember we were talking about how the rubber duck on the water wave would ride along the wave? There's your duck on top of the wave, and if you lift the duck up, the farther you lift it up, the more work you're doing and the more energy you've got. So a higher peak is going to be more energy. So this is what you expect if the light is acting like a wave. But that's not what you get. They looked at a graph that plotted E photoelectron on the y-axis versus the amplitude of the light on the x-axis, and the energy of the individual photoelectrons did not change. They just got a flat line. So they expected this, maybe not a line, but some kind of increasing curve, but they got really no change when they were changing the amplitude. And remember, the amplitude was the brightness of the light. So if you have a light dimmer on this and you try to do brighter and dimmer light and see if that changes how much energy the photoelectrons have when they're being kicked out, it makes no difference. Now, when you increase the amplitude, it does have an effect. It increases how many photoelectrons get kicked out. So that kind of makes sense. If you're turning the amplitude up, you're cranking up the height of the peaks, and it's not kicking out individual photoelectrons that have more energy, but it's kicking out more of them. So you can see your basic idea about the amplitude of the light having something to do with the energy that the light carries is right, but it's terribly wrong that the amplitude doesn't increase the kinetic energy of each photoelectron. So there's something seriously wrong here. And here's how serious it is. Your only conclusion that you can come to is that your model for the light was wrong. Light is not behaving like a wave. Here, in this case. Because if it was behaving like a wave, you would have seen this, but it's not. So what is it behaving like? Well, Albert Einstein, he was very young, he was working a summer job in the patent office, came along and explained what was going on here. Here's your metal. You got some electrons floating around in there, and instead of having a wave come in and oscillating that electron until it snaps out of the metal, he said what you're doing here is sending in a stream of energy particles. They were later called photons. He called them quanta. Let's call them photons right now. And this is kind of like a pool game. You know, you're sending in the cue ball, and it hits the ball in there, and it sends it flying. So you still get your photoelectron coming out. But this time, light is a stream of particles. Now, how come all these experiments showed light acting like a wave, and then now this one is showing that it's acting as a particle? I mean, what is different about this experiment from all of the experiments that came before? Well, in this case, you've got light interacting with individual electrons. And in all the other experiments, light was interacting on a large scale with a lot of atoms at once. So you're kind of seeing very fine-grained behavior here. The rough behavior is it acts like a wave, and the fine-grained behavior is it's actually little streams of particles. Like, I guess an analogy in real life would be something like, if you look at a newsprint picture, if you look at it under a magnifying glass, you can see it's made of a bunch of little dots. But when you stand back, you see the whole picture. You know, it fades. All the little dots are not so noticeable anymore, and they all kind of blend together to give you the picture. So that's kind of what's going on here. On a fine scale, you're seeing photons, and on a rougher scale, you're seeing more wave-like behavior. So light acts like a stream of particles when it interacts with electrons or individual atoms. It's only going to act like a wave on a large scale. So this was the problem with this. Now, here's what Einstein suggested that they do to check this out. He said, make your graph again. Put your E photoelectron, your kinetic energy of the photoelectrons, on your y-axis, just like you had it before. Now, he said down here, instead of putting your amplitude, put your frequency. And he said, here's what's going to happen. Try this. Right up until you get to the threshold frequency, which has the threshold energy. So until you reach that threshold energy, nothing's going to happen. He said, but then after that, it's going to go up like a line. And the slope on this line is a constant called h. It's Planck's constant. It happens to have a very small value. Okay. Now, so you can get it experimentally. He said, go ahead and do this experiment. And he said, here's what your energy budget looks like. the energy of the photon is actually Planck's constant, the slope, times the frequency, what you put on here. Okay, once you're past the threshold frequency, that's what it's equal to. So this is the energy of the photon. Now, you can do your energy budget, he said, if you want. This is going to hold for whenever light is acting like a stream of photons. For the photoelectric effect, your energy budget looks like E photon equals E photoelectron plus the threshold energy. Now, these two equations are the key to understanding this experiment. The first equation is the most important one. This one holds in general. It lets us calculate the photon energy from the frequency, and it's important to the idea of quantum mechanics. Quantum mechanics says things act like waves sometimes and particles other times. This connects a particle's energy with a wave's frequency. So it's a connection between those two worlds. Whenever you see Planck's constant appear, you're working in this new physics, this new quantum mechanical physics. And then this is the energy budget for this. And we're going to play with this in some of the problems that we'll do in the next couple of frames.